unit of discussions for these 2 days. I'm going to talk a little bit about pH, what it is. Then we're going to go and talk about soil clays and reactive surfaces. And then we're going to come back and talk about managing pH. You can't talk about reactive surfaces without talking about pH, so we'll introduce the concept, we'll go on to reactive surfaces, and then we'll come back to pH again. First of all, what is it? pH. Both of those terms have a meaning. Anybody know offhand? Don't look at the slide. Look at anything else. Just pH. You know what P stands for? Anybody remember? Well, H is hydrogen concentration. Somebody said something about log. Who said something about log? Huh? Inverse log. Okay, negative log. Fantastic. P stands for negative log or inverse log, and H stands for hydrogen ion concentration. You might wonder why we do this, but it'll become clear in a minute if it isn't already. P is just a mechanism used in science and engineering to deal conveniently with very small decimal numbers. Okay? And the H stands for hydrogen ion concentration, actually activity. If you know enough to know the difference between those two, I don't know what you're doing here. So I'll just act like it's concentration. But anyway, pH means the negative log or the inverse log of the hydrogen ion concentration. pH. So let's talk about some pH facts. First of all, pH and hydrogen ion concentration are inversely related, right? Because pH equals negative something. Like A equals negative D. So A and D are inversely related. So another way of saying that is as pH increases, goes from 5 to 7, 7 to 8, the hydrogen ion concentration decreases. We have some common descriptors. If things are less than 7, they're acidic. If they're higher than 7, they're basic, or in soils we often use the term alkaline. And if they're right at 7, they're neutral. Now here's where I hope you can appreciate the value of using P instead of just hydrogen ion concentration. These are the hydrogen ion concentrations in moles per liter. This is the same hydrogen ion concentration expressed in scientific notation. And here's the pH. So if your hydrogen ion concentration is 1/10 of a mole per liter, another way of saying that it's 10 to the minus 1 moles per liter, or it has a pH of 1. Well, that's not so bad, but we usually deal with pHs down more in this range. And look at all the zeros you have to keep track of when you're communicating about it. Okay? Of course, if you expressed it in scientific notation, it wouldn't be so bad, you know, but that confuses a lot of people too. So you might want to know, how can I convert from this to this? And it's really easy. It's how many places do you have to move the decimal till you get a whole number? And if you count here, you can see it's 1, 2, 3, 4, 5, 6. So this is equivalent to 10 to the minus 6 because I moved them to the right, and it's a pH of 6. So soils and other materials that we commonly deal with. Soils are on this side, other common materials over here on the right. Sodium hydroxide is a pH of 14, bleach is almost 13, milk of magnesia is about 10.5, seawater, high 8s, pure water, not in contact with air, is neutral at 7. Rainwater, even in an unpolluted area, usually is in the high 6s. If you're in a polluted area where you have sulfur dioxide or nitrogen oxides, it's more acidic than that. Some of the stuff we drink all the time, drank this morning, for example, coffee, pH of 4. Some things are stomach acid, lemon juice, highly acidic. In terms of health and safety, anything that's both, anything that's either highly basic or highly acidic, pH of 1, pH of 14, it'll tear your skin up either way. Didn't mess around with them. But just to kind of give you a frame of reference as to what some common materials are, and here's some information on soils. Forest soils in our region would probably be 4 to 5, in our region at least. Cropland in the humid regions, 5 to 7. There are soils out west that have a lot of calcium carbonate in them. They're called calcareous. They're naturally in the high 7s to mid 8s. We do have soils in the extreme, both extreme acidity. Those are acid sulfate soils. And we have some sodic soils, again, out west, sodium-affected soils, they're called sodic soils, that tend to be above 9. Very hard to manage. Water doesn't infiltrate very well. The diffuse double layer from one comes up to the diffuse double layer of the other, and they just keep the water from going through. We do have acid sulfate soils here. There's soils that where parent material that contained a lot of iron sulfide are exposed at the surface now, usually due to development or road building or something. And the sulfides quickly oxidize and turn the pH of those soils to the high 1s, low 2s. Obviously, nothing grows there. You've got to do some kind of major management if you want to get them vegetated. Okay, so question. If the hydrogen ion concentration is this, what is its pH? How many places to the right do you need to move the decimal to get a whole number? 1, 2, 3, 4, 5, 6, 7. It's pH of 7. The answer is D. That's an easy 1 point, right? Right? Say yes, Trish. Yes, Trish. Oh, but you'll have it in a paper in front of you. Okay, so now that we know a little bit about pH, let's talk about cation exchange capacity. I told you this morning that the real reactive center of soils is where solids and liquids meet at that interface. And one of the dominant things that happens there is cation exchange. We abbreviate it CEC. You know, every field has their little abbreviations that they live by. What is it? Well, it's the ability of a soil to hold cations on charged sites. It's also a measure of the net negative charge of a soil. The only reason the soil can hold cations is because it has negative charge. And it's expressed in 2 ways. I still think of the old way, milliequivalents per 100 grams of soil, or centimoles per kilogram of soil. That's the international units that we use now in science. Fortunately, they're the same scale, so the numbers will be the same. It's just the label on it, which is going to differ. Why is it important? Well, the exchange phase is the storehouse for cationic nutrients. When cations are absorbed to exchange sites, they're protected at that moment at least from leaching. They're not in the soil solution. They won't go anywhere if it rains or you irrigate. They're in a sense, protected by being absorbed onto these exchange sites. There is, however, a dynamic equilibrium between the nutrients in the soil solution and on the exchange sites. So if the conditions in the soil solution changes, there's probably going to be some changes on what's on the exchange sites also. So remember we talked about dynamic. Here's where that dynamic really is manifested. Okay, so I really think it's important to understand why soils are charged, so I'm going to spend some time talking to you about it. If you're bored by this, just forgive me, but I think it's really important. So here is a clay mineral. It's very small. It's a secondary mineral. It's also a platy mineral, as opposed to the oxide clays, another term that's used. We'll talk about the structure more a little bit later, but the fact is each of these negative charges here is a charge within that clay mineral. It's highly negatively charged. And so it is covered basically, although I couldn't quite show it that way, it's covered by a swarm of cations that are neutralizing the charge on the clay. Right? And if you add up all these little negatives, you'll see that it is equivalent to the sum of the positive charges that are absorbed on it right now. 13 calciums, where each one is +2, 4 magnesiums, where each one is +2, 2 potassiums, where each potassium is a +1, and 6 hydrogens. Okay? That's the way it is right now. If you change the soil solution, in this case we're changing it by adding a potassium fertilizer called muriate of potash, 0060 or 0062, you've upset the equilibrium. We upset the equilibrium when we fertilize. Okay, so stuff's going to shift, stuff's going to change. And I'm just talking over here about the changes in the soil solution. Obviously the soil solution has a whole soup of things in it. But we're going to kind of leave that aside and just talk about what's new, what's changed as a result of our having added a fertilizer. Okay, so we add a fertilizer to a soil that already has the charge neutralized by this swarm of cations. So what's going to happen? Well, some of the potassium that we added is going to end up on the exchange sites. That's good because that's our storehouse. Okay? But other things happen also because the cations that are here are neutralizing the charge that originated in the clay. We can't just make all 9 of these potassiums come on here without losing something that was there to start with. All right? So let's look at what happened. We started out with 9 potassiums in the soil solution, more than what we had before. After it equilibrated, we now have 2 more calciums than we had before, 1 more hydrogen than we did before, 1 more magnesium than we had before. We still have the 9 chlorides and 2 more potassiums. Not everything we added went on the exchange site. We enriched the soil solution as well as enriching our storehouse. But by enriching our storehouse with potassium, we lost some other things, didn't we? Now more calcium out in the soil solution. There's no more magnesium out in the soil solution that was on the exchange sites that was kicked off by our having added fertilizer. So I guess the bottom line is there's always consequences to what you do. It's okay as long as you understand that. But in changing the equilibrium and making your soil richer in potassium on the exchange sites, you in fact have lost some other things that now are out in the solution. And remember the fate of this: if it rains, if we get a heavy rain or an irrigation, this could move below the root zone. Of course, it's also there to nourish the plants and the microbes, and hopefully they take it up before it gets away from them. Okay, so there's an exchange. You can shift what's on exchange sites as well as in the soil solution by adding stuff to the soil, but you do it at a price, so to speak. So how do these soils become charged anyway? All right, well, there's 2 major mechanisms whereby charge develops in soils. One is called isomorphic substitution, or isomorphous, depending upon who you're reading, and it leads to something we call permanent charge. And it's the main mechanism for the layer clay minerals, what you might know as aluminosilicates. They're platy minerals. The other mechanism is due to protonation and deprotonation of surfaces. Now, a proton is nothing but a hydrogen ion. So what this means is hydrogen ions move to surfaces, protonation, or move away from surfaces, deprotonation. That's all it means. Okay? And this is also called variable or pH-dependent charge, as opposed to the permanent charge we had up here. And this is the main mechanisms whereby iron oxides, hydrous oxides of iron and aluminum, and organic matter get their charge. The charge on iron oxides and in organic matter varies depending upon the pH of the soil, because the charge is pH-dependent charge. It also occurs at the broken edges of clay minerals. And we'll have a picture in a few moments that will, where I'll point that out. Okay? So there's 2 basic kinds of charge in soil. One's permanent. It is a result of the environment in which the clay mineral formed. And the other is pH-dependent or variable charge, and it's due to the gain or loss of hydrogen ions on surfaces. So if we think back to the clay minerals, the layer sheety minerals, often called silicate clays, okay, there's 2 basic building blocks to them. They can either have a silica tetrahedron, and this is like a pyramid, and they also have aluminum octahedron that are like rectangles. And they're the basic building blocks of the clay minerals that we're going to talk about. Now, this is an example of a unit cell of a clay mineral. And I just want us to have a notion of what a unit cell is. Do you ever put salt on your food? Okay. What's the formula for salt? Do you know? Okay. NaCl. Okay. Sodium chloride, NaCl. Okay. Now, does that mean that your little grain of salt that you might see is just one Na and one Cl? No. We label minerals by the smallest repeating unit. Okay. So the repeating unit in that is sodium chloride. But in fact, that grain might be 10,000 Nas and 10,000 Cl. Okay. So same way, this is a unit cell of a clay mineral. And it happens to be a 2-to-1 clay mineral because it has 2 silica layers and 1 alumina layer. All right? Remember we looked at the building blocks. In this case, the silica layer is bonded to the alumina layer by the sharing in common of these 4 oxygens. And this silica layer is bonded to this alumina layer by the co-bonding of these 4 oxygens. So silica sheet, alumina sheet, silica sheet bonded together by sharing in common some ions. And this is the unit cell from the top to the bottom if we were to slice through it. And if you look at the charges here, you know, things have a common charge. Oxygen is -2 and silica is +4 and hydroxyl is -1. If you add all these up, you can see that you've got 44 positive charges and 44 negative charges in this unit cell. Okay? So 44 plus and 44 minus gives us a net 0. This unit cell isn't charged, neutral. But sometimes the environment in which these clay minerals form is richer. The soil solution is richer, and there's a lot of stuff in the soup, so to speak. And so it's entirely possible, if there's a lot of aluminum in the environment, that instead of having 4 silicas in the silica sheet, there's only 3 silicas, and in one of the places where there could be a silica, there's an aluminum. And they can substitute if they're similar in size. Okay? But they're not similar in charge, are they? Alumina doesn't have the same charge as silica. So charge can occur in the silica sheet. Iron can substitute for aluminum in the alumina sheet, and in this case we've got some more substitution down here, right? So what's the net result in terms of charge? Well, when you add all the positive charges up, you get a +42, and when you add the negative charges, you still have -44, right? So what's the charge on this unit cell? -2. So this unit cell would contribute charge to the clay. Now remember, a clay mineral is made up of thousands or hundreds of thousands of unit cells. Some of them might have a charge, some of the others might not as you look across the clay. But this is where this charge, this permanent charge, comes from. This happens when the mineral is forming. You don't change this by management. Clays that are in your soil are there because of parent material and time. Okay, so you can see where this isn't charged and this is, right? Okay? The richer the environment in which a clay mineral forms, the higher the likelihood that there'll be some substitution in one of those 3 layers and that charge will develop. Permanent charge will develop. In fact, an actual clay mineral is made up of a huge number of unit cells. 10,000 maybe is a good example. And some of the unit cells have charge, some don't. But the clay platelet itself is covered with a swarm of cations that neutralize the charge that originated in the clay because of the environment in which it formed. So if we were to look at this box as a clay mineral, okay, it'd be covered with exchangeable cations to neutralize whatever charge that clay mineral had because of the conditions of formation. Now the fact is there are a lot of clay minerals. People have had a lot of fun studying them and naming them, usually for themselves, but not always, okay? I'm going to give you some of the main players here. And I don't think we have much montmorillonite here, although it does show up on a map I'll show you in a minute, but we certainly have all the others. Okay, so clay. If you send your soil to a lab and you say, I want you to determine how much sand, silt, and clay is in it, they'll do that. And they'll tell you the % of clay-sized particles. But you don't know what kind of clay it is. Not from the soil analysis, anyway. If you're in Maryland, it can be, it's probably some combination of these. And notice that we have different kinds. We have one-to-one, what we call one-to-one clay minerals. One alumina sheet with one silica sheet. One pyramid bonded to one rectangle, okay? Then we have other minerals that are called 2-to-1. Like that example we just looked at, that was a 2-to-1. That 2 silica sheets with an alumina sheet sandwiched in between. Sometimes there's specific cations trapped between the 2-to-1s, as in the example of illite or hydrous mica. Sometimes stuff's just there kind of loosely hydrated, like vermiculite. Okay? So there's 1-to-1 clays, one of each kind of building block. There's 2-to-1 clays with various amounts of things going on. So you'll hear about 1-to-1 clays, 2-to-1 clays. Then we've got chlorite. That's an interesting one. That is a 2-to-1 clay with an extra aluminum octahedral sheet sandwiched in between. Okay, that's a 2-to-1-to-1. Some books call it 2-to-2, but 2-to-1-to-1 is more accurate. Now, the real thing is, how much charge do they have? Okay, because remember, clays are one of the two materials in the soil that are going to hold nutrients, cationic nutrients. Kaolinite isn't particularly highly charged. It has 3 to 15 units of exchange capacity per 100 grams of pure stuff, right? At the other extreme, look at vermiculite. Whoa, 120 to 150 power pack, huh? For 100 grams of stuff, same weight of stuff. Mica's in between. Mount Merlinite's pretty substantial. Chlorite, 15 to 40, like the hydrous mica. So some clays are much more highly charged than others. The big shrink swell clay we talked about before, remember, don't build your house on it, don't build a bridge on it. Mount Merlinite, sometimes called smectite. Smectite's kind of the group name for it. Mount Merlinite is one of the examples. Very, very, very high shrink swell clay. Now, this is an old example. It's published in '68, but this tries to give you a sense of the clay mineral suites that exist in Maryland, and this is how this reads. Well, Mount Merlinite, chlorite, vermiculite, mica, kaolinite, and glauconite. I'll come back to that in a sec. If there's only one X, maybe none, maybe up to 10%. Two X's, 10 to 30%. Three X's, 30 to 70%. And you can see that although in some cases we have a dominance of one kind of clay mineral, overall we tend to have mixtures as opposed to dominant kinds. But as a general rule, I like to think of kaolinite as being the dominant clay mineral on most of the coastal plain. Highly weathered marine sediments, the more active clays have weathered away over the eons. We certainly get younger clays, more reactive clays, but again, variable across the state. Where do you think these differences come from? Remember we talked about why soils were different? Yeah, okay. Here's a good example. Why is her hair color so markedly different than mine? Forget I'm gray, but my base color. Why is her hair color markedly different than mine? Different parent material, okay? She obviously has red hair in her gene pool. I don't have any in mine, okay? So if you look, and Gary showed you this map a little while ago, but here's another map of the Physiographic Provinces. Take a look at that, and then we'll go back and look at the clay mineral map again. See some strong similarities there, okay? These are different landforms. They're different ages, amount of time. They're different parent materials, okay? And thus, we're going to see different mixtures of clay minerals in these different regions. Primary difference between the clay minerals in your soil are what did you start from, what was your parent material, and how long have you been in the environment? How old are you? How old is that soil? How old is that environment? And we've got variations of both across Maryland. Glauconite. Let's talk about glauconite. Glauconite is actually a special kind of a mica, but it usually occurs in close association with iron sulfide. Now, sulfide's unstable when you bring them up above the water table, and the oxygen gets a hold of them. And in fact, you can see this band here, and some of these aren't far from where we are here. These are the ones that have the potential of forming acid sulfate soils if they're brought up and left at the surface. And that's been done in housing projects in Maryland. It's been done at a road cut off the Beltway in Maryland. There's a number of places where, because we've changed the way the land looks and transformed the land surface, that these deposits, which initially were 20, 30, 40 feet deep, are now at the surface, exposed to oxygen and oxidizing and forming acid sulfate soils. So that's one of the more unusual things about our Maryland map. Okay. So we've got a lot of mixtures of clay minerals in our soils. Okay, how about the variable charge sites, or the pH-dependent sites? What kind of materials do we see that? Well, hydrous oxides of iron, aluminum, and manganese. The fact is most of our oxides here in our climate are of iron. Other places, aluminum and manganese are more important, but not here. Humus, the highly weathered, highly, so I use the term weathered? Highly stable organic matrix, and also on the edges of aluminosilicate clays, okay? That's where the variable charge can develop. And it's a very different mechanism. Isomorphic substitution is when one thing substitutes for another while that mineral is forming. This is happening all the time, and it's happening as a function of the pH of the soil solution, because that's the environment these minerals are bathed in, the soil solution. All right? So how does pH-dependent charge arise? Well, remember, at a lower pH, let's say 4.5, right, there's a fairly high concentration of hydrogen ion in the soil solution. All right? If there's a high hydrogen ion concentration in the soil solution, hydrogen ions tend to associate with the broken edges, surfaces, of the oxide minerals. So in this case, there's a broken edge, and at this oxygen, 2 hydrogens are associated with it. Same thing here, same thing here. It gives the net charge of this iron oxide at a pH of 4.5 of 3. Okay? Let's say we limed that soil, and the pH of the soil solution went up. Let's say from 4.5 to 5.5. Soil solution isn't so rich in hydrogens anymore, right? So some of these hydrogens that were absorbed now dissociate, or the surface protonates. So now instead of having 2 hydrogens at every oxygen, you only have 1. So what's the charge now? 0. That iron oxide is neutral right now, even though it had a charge of +3 before you limed. Now let's say the lime hasn't all dissolved yet, and when it does, the pH is up to 6.5. Okay? Lower hydrogen ion in the soil solution, so more hydrogens dissociate from the surface or deprotonate. Now we just have the oxygens exposed with no associated hydrogens. Now we've got a -3 charge on our iron oxides. Now we have iron oxides in our soil, and we lime fields every year to raise them from here to here. So cation exchange capacity is not a constant in our soils if we have humus or iron oxides, because these guys are on the roller coaster. Okay? pH drops, there's more positively charged iron oxides. As the pH goes up, you probably go through a range where it's neutral, and if the pH goes high enough, they're actually negatively charged, just like your clay layered clays. Okay? pH-dependent charge, variable charge. Charge that varies as a function of the pH of the environment in which the material is bathed. Different than permanent charge. Doesn't matter what the pH is. That charge originates because of the environment in which the mineral formed and substitutions that occurred then. This is happening every year. Okay, so that's how it occurs on iron oxides. This is what happens on a humus molecule. This is a very simplified diagram of a humic material. And this is interesting for a couple reasons. First of all, it kind of shows you how humus is built. These are little aromatic groups, for those of you that took a little bit of chemistry. These are aromatic groups. There's bridges between them. These are called bridges. Okay? And then there's functional groups off of them. Okay? So all these functional groups could potentially have a hydrogen that dissociates from them as the pH of your soil increases. And you can see that a typical humus molecule has all kinds of functional groups, and the different groups have different neighborhood associations. Like this particular group has a carboxyl acid with 2 hydroxyls, whereas this one doesn't, but it has one over here close to it. And the complexity of who you're with, as well as who you are, affects when you're going to lose the hydrogen ion, or at what pH you're going to lose the hydrogen ion. So what happens is, as the pH increases, various groups, like maybe the hydroxyl group loses it first. The hydroxyl ions that are out by themselves, not near anything else, lose their hydrogen. What's going to happen if this baby loses its hydrogen? It's going to be a negative charge, right? Because right now that hydrogen +1 is neutralizing, but if the hydrogen +1 moves away, this site's going to have a -1. And then let's say the next thing it loses is the, is there an isolated carboxyl? We'll take them over here. Let's say at another pH, the carboxyls next to carboxyls lose it. Okay? Well, again, if that hydrogen moves away, the surface is deprotonated, there's going to be charges here. So humus this is actually only a fraction of what an actual humus molecule looks like. It's probably 1,000 times this size, okay, with aromatic groups and bridges all over the place and active functional groups all over the place. And as the pH changes, different groups lose their hydrogens, okay, or as the pH goes down, different groups get hydrogen moving back on the surface. So this is another roller coaster. But that's how pH-dependent charge arises on a molecule of humified organic matter. Gain or loss of hydrogen ions at surfaces. In this case, the gain or loss of hydrogen ions at what we call functional groups. Okay, so let's compare the two materials we just talked about with some of the clay minerals we looked at in the last table. So colloid, that's just a term for very small clays that can stay suspended in water and demonstrate a whole array of physical characteristics. Humus is our organic colloid. Okay, then we've got 3 layer minerals: vermiculite, montmorillonite, illite, and then iron oxides. So humus, look at the charge on this baby, 100 to 300 units of charge, centimoles per kilogram or milliequivalents per 100 grams of stuff. Much more highly charged than even the most charged of the clays. Can go up to 300. Vermiculite, very power-packed. Montmorillonite, very power-packed. Illite, pretty good. Iron oxides, though, even at a pH of 7, and remember we've got to state our pH here, we can't talk about it at all, isn't very charged compared to either the layer clays, the aluminosilicates, or the humus. So iron oxides do have some charge. I mean, it's not insignificant. It's way more than our sands and our silts. But on the same scale, comparing it to the layer clays, the aluminosilicate clays, or the humus, it's nowhere near as power-packed, so to speak. Now, all that data was for pure clays, 100 grams of pure clay. In fact, our soils don't have 100 grams of pure clay. They're mixed in with sand-sized particles and silt-sized particles, too. And let's go back to our textural class delineation now, and let's see what typical cation exchange capacities would be of real soils, which are mixtures of sand, silt, and clay, and also have some organic matter in them. And there's some pretty wide ranges here. Sands, you actually have a sand textural class over in that lower left-hand corner of the textural triangle, only between about 1 and 5 units of charge, milliequivalents per 100 grams or centimole per kilogram. Fine sandy loams, we've got those over on the shore, 5 to 10 units of charge. Loams and silt loams, 5 to 15. Clay loams, 15 to 30, and even the clays, above 30. Why the wide range? Well, we don't know how much organic matter is in those real soils, and that's going to affect it. We also don't know what kind of clay is in there. Remember, all you know from the soil lab report is how much clay you got. You ask them to do a hydrometer, pay that extra 15 bucks, they're going to tell you the percentage of clay, but they're not going to tell you what kind. But as a general rule, the more clay you have in a soil, the higher your cation exchange. Some labs report cation exchange routinely in a fertility test, but many of them don't. If I had some new land, I'd look at it, just for the heck of it. Then I suffer from morbid curiosity. Okay. Factors affecting CEC of the soil. Why do soils have different CECs? Well, they could have different amounts of clay-sized particles. If you've got a silt loam, it has more clay in it than a sandy loam does. One reason. Another reason is the kind of clay. Maybe you've got a soil that's dominated by kaolinite in one case, but has illite or vermiculite in another case. Got vermiculite, it's going to have a whole lot more charge. Okay? Amount of humus. Okay? Does it have 1% humus, 3% humus? Huge difference. And then, what's the pH of your soil? All of those things affect the cation exchange capacity of soils. Now you might ask yourself, oh, how much of a difference does it really make? You know, so here's some old classic data from Pratt. He was a big soil chemist at University of California, Davis. and he published this stuff back in the 60s, he and a grad student. They actually took 5 soils from California and measured the CEC at various pHs. Now, they're not saying that the pH of the soil is at any of these pHs, but they basically manipulated the solution they were extracting the soil with at various pHs so they could look. So you can see that the pH here goes from 3 to about 8. Under natural conditions in the environment, it would be unusual to have something below 4, even in a forest soil. So this is probably more ecologically realistic. Although they certainly have conditions there where the soils are going to be above in an alkaline area. Okay, so let's look at this one on the bottom. Okay, they measured it at 3, 3.5, 4, 4.5, 5, 5, and it's very precise. This took them a long time. Okay, and expressed the CEC at either one. So at a pH of about 3, it had a CEC of, I'll say, I don't know, 2.5 or 3. I'm eyeballing it here. And maybe at 8, it went up to maybe 5, huh? Went up some. Is that drastic? Noticeable? I don't know. Okay, not a very steep slope here, right? There wasn't a huge change. Let's look at this one in the middle. At a pH of 3, this soil had a CEC of, I'll say, maybe 12. And at 8, it went up to, heck, I think that's 30. You agree? That's pretty drastic? Oh, yeah. What do you suppose could account for that much of a change in pH? You had to hypothesize. Might have been high in organic matter? Yeah, you think? So in some cases, the amount of change you see between where you let your soil get to when you let your pH drop and where it gets to in terms of pH after you lime, let's say 5.5 to 7.5, and that's probably what typically happens here between liming events, it can be pretty significant in terms of the amount of cationic nutrients your soil can hold. Is it always? No, it depends upon your soil properties. No? But it certainly can be in some cases. So this is one of those classic kinds of studies that people don't do very often. I mean, I'm glad we have an example of it at all. No one's ever, I don't think anyone besides Pratt has ever looked at specifics over soils. Okay, another concept you might want to become familiar with is something called base saturation. And base saturation looks at the percentage of your exchange capacity that's occupied by basic cations. And calcium, magnesium, potassium, and sodium are all basic cations. Hydrogen and aluminum happen to be considered acidic cations. And as a general rule, the greater the base saturation, the more fertile the soil. Now, there are soil testing systems, and I believe Josh will talk to you a little bit about this later this afternoon, that use base saturation as their criteria for recommending nutrients. Most land-grant universities don't, but there are some private labs that do. They act like there's some magic base saturation that's important and some magic calcium-magnesium ratio that's important. And it's out there. I don't espouse to it, but those thoughts are out there. But what might you want to know about base saturation? Well, first of all, you might want to know how to calculate it because it's fair game for the exam. And I'm trying today not only to give you a sense of the science concepts you need for the exam, but give you a little clue on some of the potential questions. So let's look at this example. First of all, some labs routinely report base saturation, others don't. Depends upon what lab you decide to use. But let's say that if they did, they extracted all the exchangeable cations and they expressed them on the soil test report in terms of centimoles per 100 grams of soil. If you got information from your lab expressed like this, you could do two things with it. You could figure out the CEC of your soil, and you could also figure out the base saturation. Okay? Now remember, the cation exchange, or CEC, is one way of measuring it is by extracting all your exchangeable cations and expressing them as centimoles per 100 grams and adding them up. Okay? So we could certainly do that with this data, right? Because we have a very complete list of exchangeable cations. So there's 3 centimoles of hydrogen per 100 grams, There's 12 centimoles of calcium per 100 grams. There's 5 centimoles of magnesium. There's 1 centimole of sodium and 4 centimoles of potassium. So what's the CEC of that soil? In centimoles per 100 grams of stuff. All you have to do is add them up. They already expressed them in the right units. 25. This soil has a CEC of 25 units of charge, centimoles, per 100 grams of stuff. Right? If it's expressed in this way, if you get your data in centimoles per 100 grams of soil, all you have to do is add them up. Now, can we figure out the base saturation? Can we identify the bases, first of all? Let's go down the list. Is hydrogen basic? No. Calcium basic? Yes. Magnesium? Yes. Sodium? Yes. Potassium? Yes. So what's our base saturation? As a percent. 22 of 25. A percent is parts per 100. 25 is a quarter of that. How about 88? Okay? Our base saturation is actually 88%. 22 divided by 25 expressed as a decimal fraction is 88. So this soil has a CEC of 25 centimoles per 100 grams and a base saturation of 88%. That's a nice fertile soil. What happens in those acid sulfate soils I was telling you about, where you bring up a sulfide material and leave it near the Earth's surface and it starts to oxidize, is you'll see base saturations down about 10, 7. Somehow, by mistake last summer, a lab sent me the lab report from the Bureau of Mines. Now, I don't know why I got it. I called them about it because I didn't want them to send me the bill. I appreciated getting the report, but I didn't want the bill. But they were clearly looking at acid-affected soils. And the base saturations were literally 8, 10, 12. Lots and lots, huge amounts of exchangeable aluminum and exchangeable hydrogen. They apologized, and I filed that away as a real-world example of what acid sulfate soils can look like. So if you get an example like this, don't be thrown by it. Remember that CEC is expressed in centimoles per 100 grams. If they gave you this on some other weight of soil, just express it on the basis of 100 grams. If they give it to you in centimoles, you're set. If they give it to you in milligrams, you're screwed. I'm not going to teach you how to do that. That's not for today, okay? All right, let's go back and talk about acidity again. First of all, we distinguish between 2 types of acidity in soil, active acidity and reserve acidity. Active acidity is the hydrogen ion and aluminum ion in the soil solution, okay? But reserve acidity is the hydrogen ion and aluminum ion on exchange sites. Now, this is a pretty good example of 2 different soils. Take A and B. These are 2 different soils that have about the same active acidity. That is, the liquid in the serving arm of this little coffee urn is about the same level. But you can see that they don't have the same amount of reserve acidity. Chances are this is a soil that might have a CEC of 5, and this might have a CEC of 15. So there's a lot more reserve acidity here in soil A than there is in soil B. That's why if you have differences in soil texture across your fields, you don't want to necessarily follow the lime recommendation for your silt loam fields on your sandy loam fields, because you could run into problems with over-liming. But a point this does make, and why we all like this coffee urn example, is the neutralization of acidity occurs in the soil solution. But if you neutralize all the hydrogen in the soil solution, what's going to happen? Well, it's going to be recharged by what's in the coffee pot and the reserve acidity here, right? And so you'll neutralize it again, and it'll move out again, and you'll neutralize it again. And eventually, after this cyclic multiple neutralization, this will drop down because the reserve acidity drops down. And that's essentially what happens when we lime. Thousands of times this happens. Neutralize what's in the soil solution, some hydrogen moves out from the exchange sites. We neutralize it again, some more hydrogen moves out. Over and over and over again, slowly. Okay, so let's think about why our soils are acid. Okay, some of you have experience with soils that aren't acidic naturally. What are the soils in Missouri? 7. Do they have any calcium carbonate in them? Yeah. Okay, so there are places, particularly west of the Mississippi, where it's drier. We don't get as much rainfall as we do here, where our soils, our naturally occurring soils, are neutral or basic. My husband and I had 10 acres of land out in Rio Grande Valley, south of Las Cruces in the 70s, and that was a Glendale silt loam, and it had a pH of 8.6. 10% calcium carbonate in that soil, in the clay size fraction. Beautiful soil, best soil I've ever had. Okay, but they only got 10 inches of rain on average. Stuff didn't leach. So we have acid soils back here because acidity, there's reasons why acidity is always being formed, and there's nothing to neutralize it. We don't have calcium carbonate in our soils to neutralize it. We have to add it as lime. Nitrification is one of the big reasons why soils have acid material in them. This is basically the oxidation of ammonium. Josh is going to talk to you about that a whole lot more. Doesn't make any difference where that ammonium comes from. It could come from fertilizers. It could come from manure. It doesn't make any difference. But there's 2 units of hydrogen produced for every 1 unit of ammonium that undergoes this process. So it's a 2-for-1 deal here. There's also a whole host of organic acids produced by plant roots and microbes. Some of these exudates we talked about are acidic. It's actually a mechanism whereby both can make materials more available to them, especially things tied up in minerals. Rainfall is slightly acidic due to the reaction, the solution of carbon dioxide in rainfall to form carbonic acid. In areas where you've got a lot of vehicular traffic, you get nitric acid, and in areas where you've got sulfur dioxide from burning coal, for example, you can have sulfuric acid. I don't think we have much of this anymore. I think most of the coal-burning plants that burn high sulfur coal have had to put scrubbers on. But we certainly have this in our region where there's a significant amount of nitrogen coming into the system from vehicular traffic. Aluminum, and aluminum's in our soils because aluminosilicate minerals weather, break down. They release aluminum into the soil solution, and aluminum undergoes a reaction called hydrolysis. There are 3 hydrogens released from hydrolysis for every 1 molecule of aluminum that hits the soil surface. So this was a 2-for-1, and this is a 3-for-1. If sulfur or sulfide, like the iron sulfide with glauconates, or sulfur, elemental sulfur, is released into the soil, we have 2 units of hydrogen produced per 1 unit of sulfur. So bottom line is there are processes going on that release acidity into the soil solution. If you have certain kinds of pollution in terms of vehicular traffic, or you have unusual conditions bringing reduced sulfur up, it can be worse. We also have a lot of rainfall in our area, so it leaches the bases away. There's nothing in our soil naturally to neutralize the acidity the way there is in the drier parts of the country, and so our soils tend to become more and more acid with time. Does it make a difference? And this is a diagram. There are many versions of this in different places. You have one of these on page 76 of your handbook, but I took the example out of Brady and Weil's book. This is a pH from 4 up through 9, and we're looking at a whole bunch of either nutrients or microbial components. And the thicker the line, the more there is. The thinner the line, the less there is. Let's look at zinc, which is right here, easy for me to reach here. You can see that there's more zinc, available zinc, at a pH of 4 than there is at 7, although we're not in trouble yet. But you bring that soil up to 8.5 or 9, and what do you think can happen up here? Zinc deficiency, okay? It's not available. Boron, same thing, pH-dependent availability, more in the near neutral range, less at either high pH and low pH. Let's see here. Oh, here's a nice one. Manganese and iron. Look, think you might have iron and manganese deficiencies at a pH of 8.5? Yep, good. But you've got lots of availability, high availability where we typically keep our soils if we're liming typical soils. And look what happens down here. Okay? Lots. Actually, you can have toxic levels of iron and aluminum in highly acidic soils. Okay? They're nutrients, plants need them, but too much isn't a good thing. And down here, they can reach a phytotoxic level, a plant toxic level. Okay? Here's an interesting one, aluminum. You don't see much soluble aluminum at a 6, but as the pH drops down to 4, again, solubility of minerals increases at a lower pH, and the aluminum, which is not a nutrient, can reach toxic levels at low pH. So we can have problems with too much aluminum, too much iron, too much manganese at low pH. If you look at, here, calcium, magnesium, potassium, these are all bases. Notice how they tail off to very low levels at low pHs. That's because they've probably been leached away. They're dominant players in the soil solution. As things get more and more acidic, they're bounced into the soil solution and they leach away. And notice the biological things up here. Do fungi care what pH it is? Nope, they don't give a flip. Okay. Bacteria, however, do. Right below about 5.5. The most common bacteria aren't as happy. They're not as active. That's one of the reasons why we want to lime a soil if we're going to grow a legume and we're going to rely upon nitrogen fixation. We want the soil environment to be optimal for the bacteria whose work we want to prosper. Okay? So if we're growing alfalfa, which has even more picky bacteria than soybeans, we probably want to lime to 7 so to keep those rhizobia happy. But even if we're growing soybeans, we probably want it up about 6.5. But below 5.5, those same bacteria are less active. You're just not going to get as much fixation. I'd have a functional understanding of this or the next graph for the test. Here's another way of looking at the same thing. It's called Why Do We Lime? Why liming to reduce acidity is often helpful. Well, let's look at this. Liming is going to eliminate that soluble aluminum. Remember how that got big, blew up as you had acidic? You want aluminum. Aluminum's bad for plants. It's bad for us. Aluminum causes something like clubbing of roots. Roots just stop growing and they kind of end. They don't grow out and explore a lot of the root environment. They can't access as many of the nutrients. They can't access as much water. You don't want that, all right? Well, liming will eliminate that soluble aluminum that we saw in that graph. It will reduce the availability of manganese, zinc, copper, and iron. Remember, manganese and iron in particular can reach phytotoxic levels. You don't want that. You want enough, but you don't want too much. So you do want to reduce that a bit. It ensures the precondition for bacterial nitrogen fixation. Okay, so your soybeans, your alfalfa can grow well. It maintains an adequate supply of calcium and magnesium. Remember, they got leached away when the soil became more and more acidic. And it increases the availability of phosphorus and aluminum. Phosphorus and aluminum are, phosphorus and molybdenum are tied up very tightly on iron oxide surfaces in low pHs. They're there, but they're not an available form in the soil solution. Right? If you raise the pH and the charge on the iron oxides changes, the phosphate and molybdenum will come back into the soil solution. So this and that other graph right before it are very important in terms of understanding why it's important to lime and which players are affected in which way. Whichever one of these resonates with you, spend some time understanding it in case you get a question related to this thrown at you during the exam. Okay. Crops have preferences for pH ranges. Okay. Right here we're showing alfalfa up pretty close to 7. Remember, you're going to put that crop out and it's going to grow for a number of years. When you're starting out, you want to shoot to near 7. And this is pretty much a preference for the rhizobia. Soybeans, more tolerant, 6, 6.5. Tobacco, lower. Potatoes, wide range, pretty low. With potatoes, I think it's a disease control thing. We've got a potato expert here. It's to control Streptomyces scabies, isn't it? Yeah. Okay, and wheat and corn, again, that kind of range where we try to keep most of our agricultural soils anyway, 6 to 6.8. Okay, so in our recommendations in Maryland, we actually have various target pHs. Now, this is the pH we use as what we're shooting for when we make a recommendation. Alfalfa establishment is 7, tobacco 5.6, potatoes 5.2, and most other agronomic and horticultural crops we're going to shoot for 6.5. I have to tell you, I'm astounded at how many low pH soils I find in the plans and recommendations I end up reviewing. I don't know why anybody would try to grow corn on a soil that only had a pH of 4.8, you know? And then they tell me they have 180 bushel yield goal, and I'm going, I don't think so. You know? Not unless you're willing to do a lot more to that soil. Huh? Okay, adjusting soil pH. You know, again, in our climate, our pH tends to be too low. We have too much acidity, and we add lime materials to neutralize acidity and to raise the pH. There are acid-forming materials that you can use to decrease your pH. Okay, you can use elemental sulfur. You could use iron sulfate or aluminum sulfate. Iron and aluminum both undergo hydrolysis and produce acidity. Would a commercial farmer use an acid-forming material? Well, he'd have to have his head examined. But some people do it for horticultural crops and homeowner basis. Another New Mexico story, but there were people that moved out there from places where they associated azaleas with spring. Now, azaleas need really acid soils. Remember I told you what the pH was? 8.6. You know what happens if you plant an azalea in those soils? It's dead in a year. Okay, so they go into their home and garden center and say, well, I really want to grow azaleas. I've always had azaleas. My mother sent me an azalea. What do I have to do to grow azaleas? And, you know, the home and garden center would sell them some elemental sulfur, and they'd plant it, and the azalea would grow for a couple years until the stuff got used up, and then the azalea would die again. So, is lime required in a particular situation? Well, you have to know what crop you're going to grow and what its optimal pH range is. What does my crop need? Right? And you have to know the pH of your soil solution. What is your active acidity? If the pH of your soil solution is less than the optimal range for your crop, then you know you need to lime. But that only answers that question, do I need to lime? The next question is, how much lime do I need to apply? And in order to answer that question, you have to know more stuff. Yeah, you have to know your target pH and the pH of your soil solution, but you also need to know your reserve acidity. Know how much. Right? Now, a lime requirement. That's a process or a test which estimates the amount of pure fine limestone you need to raise your soil to your target pH. So it can be a process or a test. Okay? I'm going to talk for a couple minutes about the tests. There's a lot of lime requirement tests out there. They're usually called buffer tests. You mix your soil with a measured amount of a carefully designed buffer. You let it equilibrate. Most of them are between 15 and 20 minutes. And then you measure the pH of that buffer. And the more the soil lowers the pH of the buffer, the more lime you need. It's a quick way of determining your lime requirement. So I'm going to tell you just about a couple. SMP. Remember I told you people name things for themselves? Well, here's a perfect example. These are 3 soil chemists, Schumacher, McLean, and Pratt, the SMP buffer. It was developed for Midwest soils, soils that had a high organic matter content, a lot of clays, a lot of 2-to-1 clays. A lot of soil test labs used to use SMP buffer. Adams was a big deal soil chemist at Auburn, and he found that SMP over-limed ultrasols in the southern United States. And he developed his own buffer, Adams-Evans buffer. And now there's Malick buffer. And Malick buffers for large port now has replaced the SMP buffer, which had 2 chemicals in it, which caused the residues of the soil to be considered hazardous materials and caused a lot of disposal costs at the labs. So now people use Malick 3, which gives approximately the same lime requirement as SMP. Here's just an example of how the Adams-Evans buffer could be interpreted. First of all, you've measured the soil pH in a water suspension of your soil. This would be your active acidity. So you know that. In this case, the target pH is 6.5. This buffer is made to be a pH of 8. So if by mixing your soil with it, it lowers the pH, it indicates there's reserve acidity there. So if you had a pH of 5.9 in water, and it lowered the buffer pH to 7.3, you'd know that you'd need about 1.5 tons of lime to reach your target pH. So depending upon what you're using, there's either equations or lookup tables. Actually, your soil test lab tells you this, but you might have wondered when you look at your soil test lab, why are there two pHs? Why is there a buffer pH and a water pH? Well, that's why. They're using some buffer, and they're telling you the pH of the buffer. Now, they often don't tell you what buffer they use. You can't interpret it, but they often give you the lime requirement in addition to the pH of the buffer solution. Okay, texture and lime requirement. For any specific pH, how much lime you're going to need is going to depend upon your reserve acidity, and that's going to be reflected also in your soil textural class, where a clay loam soil is going to have more reserve acidity than a sandy loam and more than a sand. And this diagram, and this is the one I don't know where the hell I got, or I'd give the reference here, you can see where, let's say at a pH of 6 with a CEC of 5, a half a ton of limestone on this one has a pretty dramatic effect, whereas a half a ton of limestone on one of these soils that has a higher CEC doesn't have anywhere near the effect. Again, I hope you get a sense also of if you were to add the same amount of lime to a sandy loam that you added to your clay loam, you could get yourself in a difficult situation pretty quickly. Okay? That's why if you're going to lime according to your soil test. Overliming, if you think back to that diagram, what does overliming do? Well, it really messes up your micronutrient metals. Remember, they really thinned out as you went over towards 7 and 8. You don't want to add so much lime that you induce micronutrient deficiency. Okay, how often is lime required? Well, we're kind of on that roller coaster. I used that term before when I talked about pH-dependent charge. We're on a roller coaster here. We add lime, it increases the pH, but then it drops. And we lime again, okay? Does this look like a roller coaster? Okay, well, this is the soil pH, but you could have you could just as easily put pH-dependent charge on there, or CEC. You know, they're all on this roller coaster as a function of the hydrogen ion concentration in the soil solution. It dissolves, it neutralizes, stuff's leached away, pH starts dropping again, we get to the point where we have to lime again. It's not uncommon to have to lime every 3 years here in our climate. I'll bet most people that you know lime every 3 years. Other parts of the country you can lime less frequently, but not here. Big argument about when to lime. Some people say, you know, if you don't do it ahead of time, it hasn't dissolved, it doesn't do any good, blah, blah, blah. Yeah, 2 to 6 months ahead is really good, particularly if you're going to plant a very sensitive crop like alfalfa. But Mark Elliott, VPI, did some work back in the early 90s where he looked at adding lime at planting. You know, and I guess the question was, is it better to lime at planting than not at all? And I think I'm going to have to agree with him that it's better to do it at planting than not at all. Okay, this is alfalfa. That's a very sensitive crop. Remember, the rhizobia that live with it like a higher pH. It's not high enough. They're not going to fix nitrogen, right? Because they're not happy. And this was applied at planting, and this was the first year. So you don't get a lot of yield anyway the first year of alfalfa. So don't get too disturbed about the yields here. But you can see that that if he didn't if he didn't add any lime at all, the yield was pitiful. And certainly by increasing the lime rate, and I believe in this case the lime recommendation was pretty high, you do get some in-season response to lime. Now this was a good quality lime, and I'll talk more about lime quality tomorrow. 50% of this lime passed 100 mesh. This was a good quality lime. But the fact is, if you've let it go or couldn't get out in the field or couldn't get a hold of the lime or whatever, it's better to lime at planting, especially for a sensitive crop, than to not lime at all. Okay, review question. Cation exchange capacity is affected by which of the following? Amount of clay, type of clay, amount of humus, pH, or all of the above? All of the above. Exactly. Exactly.